Hello. This video summarizes our research about Bayesian network models used for contextual versus non-contextual driving behavior assessment. This research is designed to quantitatively demonstrate the potential significance of the contextual driving behavior analysis adopted in the PAYDAYS project. In most current driving behavior research, the motion of a vehicle, described by vehicle kinematic parameters like speed, acceleration, and deceleration, is relied on to measure driving behavior, which could be referred to as a non-contextual driving behavior approach. Research utilizing a non-contextual driving behavior approach has its limitations because it merely applies vehicle information, but neglects to consider the surrounding environment of the driver that may contribute to crash risks such as road conditions and dynamic traffic flow information. For example, if a driver is observed to be consistently driving at a speed much faster than others around him or her, it is reasonable to assume that this driver is driving more aggressively than other drivers. Following this rationale, we propose to define contextual driving behavior by incorporating both habitual driving behavior and instantaneous reactions under various contexts. There are three main objectives in this study. First, we evaluate the benefits of utilizing context-relevant information in the driving behavior assessment process. Second, we recognize the challenges in information aggregation and the various data size volumes for each driver, and we establish methodologies to extract contextual and non-contextual driving behavior from the detailed longitudinal vehicle telematics data at the GPS point level, combined with corresponding contextual and spatial temporal features at the road segment level. Third, we relate individual driving behavior with crash involvement frequency when data is aggregated at the driver level. In order to address the objectives identified previously, a hierarchical Bayesian network model is proposed as the methodology foundation, with the vehicle trajectory data and corresponding spatial temporal contextual data as inputs. The reasons for utilizing the Bayesian network model include the following. First, in order to investigate the relationship between the GPS level data and the driver level crash risk, we require an appropriate information aggregation scheme. Regular regression approaches have difficulties aggregating GPS level data with individual level data. Additionally, each driver has a different volume of GPS level data in the data collection process. Some individuals drive more and may have a higher volume of GPS level data, while some others may have relatively lower GPS level sample sizes. Such data volume variety will result in different levels of confidence for different individuals in the study. The Bayes rule handles the data volume variety perfectly. The posterior distributions depend highly on data volume and gives us confidence for each individual. Lastly, compared with other heuristic algorithms such as neural networks, each node in the Bayesian network model can have its own distributions, which makes it intuitively explainable. Therefore, the driving behavior and its relationship with road safety can be explained from the model results. The structure of the Bayesian network designed for this study is illustrated in the figure on the slide. The shaded nodes are observed information, including GPS level and driver level characteristics, as well as the self-reported number of crashes. The unshaded nodes are the hidden attributes, including driver behavior, driver crash risk, and the model coefficient representing the relationship between driving behavior and crash risk. The arcs and hidden nodes link all of the observed information together to construct a complete BN model. From training a Bayesian network model, the posterior distribution of hidden nodes can be learned. Using the Bayesian network models, we compare the results between the contextual model and the non-contextual model. In the figure on the left, the x-axis represents the self-reported risk, and the y-axis represents the estimated risk. The contextual model is in red, and the non-contextual model is in green. The figure shows a stronger correlation between self-reported risk and estimated risk in the contextual model. Numerically, the correlation between the real and estimated risk is 0.576 for the contextual model, which is significantly higher than the 0.143 for the non-contextual model. Additionally, the figure on the right-hand side shows a cumulative distribution of the estimation error. The black curve represents the full contextual model, and the red curve represents the non-contextual model. This figure shows that the modeling error from the contextual model is more concentrated in the low range level and that the estimated risk from the full model has less errors when compared to the non-contextual approach. Another benefit of the Bayesian network is that individuals' risk assessment can be assumed to have a distribution instead of a single value, which enables more accurate risk analysis. This is particularly useful as two drivers can have the same average estimated risk, but different distributions, which indicates different levels of risk. The beauty of the Bayesian network model is that such distributions can be continuously updated with improved accuracy when more data becomes available. The number of GPS points per individual also matters. To demonstrate this effect, we firstly perform an analysis to investigate the relationship between data size and the variance of estimated risk for each driver in our dataset. The figure on this slide shows that the variance is smaller for individuals with more GPS points, which indicates a greater accuracy of the risk assessment for drivers who have more driving data available. We also compare the risk density functions of two individuals with similar profiles and identical crash histories, but different data sizes. An illustration of risk analysis control utilizing distributions instead of mean values is demonstrated in the figure. The black curve stands for individual A with 111,490 GPS observations, and the red curve stands for individual B with 686,355 GPS observations. The estimated average risks for these two individuals are very close to each other. However, if we examine their distributions, significant differences can be found between the two individuals. As can be observed from this figure, the estimated risk density curve for individual B is more concentrated, which indicates a smaller estimation error. For example, if the 95% quantile is used for risk control purposes, the corresponding upper bound risk for individual A will be greater than that for individual B. This demonstrates the advantage of the Bayesian network modeling approach by using a distribution instead of a mean value to describe a driver's behavior. From an application standpoint, this mechanism also indicates a practical and flexible way of implementing an online or offline driving behavior assessment model. When a new individual enters the system, the Bayesian network model can provide a preliminary estimation based only on the driver's individual level profile data. As GPS information on the individual is collected over time, the confidence level on the driver's driving behavior assessment can be improved as the volume of GPS data increases. Additionally, several research findings can be drawn from the modeling results. First, the more frequently a driver changes their speed on the freeway, the higher crash risks they suffer from. Similar variables related with other types of roads are not significant in the model. Also, according to the speeding value at row number 3, driving faster than the speed limit is negatively related with crash risk, indicating that driving at a speed lower than the speed limit on a ramp may be associated with a higher crash risk. In addition, based on row number 4, it is found that drivers who drive at a speed faster than others on the ramp are more likely to have a higher crash rate. We can also find that age has the strongest significance out of the other variables, and young drivers are considered to have the highest rate of crash involvement. Unlike results from other studies, this study suggests that female drivers tend to have higher crash rates than male drivers, which is likely due to the dependency between variables. This means that risky driving behaviors of both male and female drivers have been captured by other variables already. The impact of vehicle miles traveled is positively related with crash risk, indicating that the drivers who travel more are more likely to be involved in crashes. To summarize, the Bayesian network model, incorporating both regression models and an information aggregation mechanism, is proposed as the methodology foundation in order to investigate the relationship between GPS driving observations, individual driving behavior, individual driving risks, and individual crash frequency. Based on such a Bayesian network model, we demonstrate the benefits of utilizing context-relevant information in the driving behavior assessment process when compared with prior studies without contextual information. In the case study section, vehicle kinematics data and simultaneous context-relevant information is collected from 521 drivers, together with their self-reported crash involvement. The modeling results from our sample show that analysis done with context-relevant data proves to be much better than that without context-relevant data. The results from the contextual behavior assessment model reveal that driving at a speed faster than others on the ramp is significantly related to a higher crash risk, and that a speeding value and driving faster than the speed limit are negatively related with the crash risk. This indicates a relatively lower speed under the speed limit on the ramps may be associated with a higher crash risk for the driver. The risky drivers are found to have more rapid acceleration and deceleration on the freeway, which are defined as kinematic event frequency. Besides these driving behavior indicators, younger female drivers with more vehicle mile traveled are shown to have higher annual crash rates. In addition, we demonstrated the benefits of assessing individual risks with a distribution instead of a single value, which enables more accurate risk analysis. This is because two drivers can have the same mean estimated risk, but have different distributions, which indicates different levels of risk. Thank you, and should you have any questions or comments about our research, please do not hesitate to contact us via the information provided on the slide.